Okay, so what I want to talk about here has to do with covariance and correlation. This is useful for two parts here at the end of the course. One part has to do with the thing that in the notes is called interesting association rules. The other part has to do with principal component analysis. So after we talk about a little bit here at the start about just the basic definitions of correlation, at that point you're good to kind of ignore the rest and then look at a principal component analysis video in Wicca that I have. For the association rule stuff, this whole video is relevant. So that being said, once again, remember, this is what we care about for right now, or I do at least, covariance and correlation. They have very similar definitions, that they're going to be the average of some stuff. And really the only difference is, well, what's the stuff that's being averaged? For covariance, it has to do with deviation from the mean. So we're going to think about having two features, x and y, and so then these are the values for two different features. Although technically it really doesn't even matter if they're different or not. So I'm just going to write our values for two features. So the deviation in that value is going to be how far above or below the mean it is. That's what we mean by deviation in all of this stuff. And so if we get a positive deviation, that means we're above the mean. Negative deviation, we're below the mean. So the covariance is defined for two features as the average of the deviations, which is kind of a weird thing to say. It doesn't really make any sense if we say it like that. But what this boils down to is we want to know if x is above the mean, does that mean that y will be too? Or is it the case that if x is above the mean, that doesn't tell us anything useful about whether y is above or below the mean? So the way we think about these things when deviations is involved is that there's kind of three possibilities. One is that if x can be positive, then y is negative, or vice versa. And it could be that if x is above or below the mean, then we don't have a clue at all what y is going to be. We don't get any new information. Or it could be that if x is going to be above the mean, then y is going to be above the mean, and or vice versa. So if we want to put vice versas in, we could tend to use kind of a notation like if x is above the mean, y is going to be below. If x is below, y is going to be above. Or if x is above or below the mean, we don't know what the heck y is doing. And then finally, if x is above the mean, y is above. If x is below the mean, y is below. And so what we would call these three cases is we would say that, well, if knowing something about x doesn't tell us anything about y, we would say they're uncorrelated. If they're opposite, but knowing something about x does tell us something useful about y, then we would say they're negatively correlated. And then finally, in this case, we would say they're positively correlated. And basically we think of that, if x goes up, y goes up. X goes down, y goes down. And so that's the reason that these products matter. That's why they actually tell us something useful. Just by calculating the average of these deviations, we get this neat kind of information. So the correlation is defined as the average of deviations. The only difference is it's based on z-scores. So we calculate the z-score for x, the z-score for y. And correlations are actually more useful than covariance, but covariance is kind of the starting point for the definition. So that's why we talk about it first. And so the reason that correlations are useful is because we can just kind of look at the value we get. We get a number for this. This is for numerical features, and we get a number back. But the reason it's useful is that if we look at the correlation and we get a negative number, we get something less than 0, then we know it's negatively correlated. So that means x goes up, y goes down, or vice versa. If we get a value that's 0, then it's uncorrelated. And so that means knowing something about X is useless for Y. If you think about, well, does that matter for data mining? And you can say, yeah, it does, because if knowing something about X doesn't tell us anything about Y, then what we end up with is an association rule that won't tell us anything useful. So positive correlations tend to correspond to good association rules. So the problem with that, or the thing we have to deal with, is that when we talked about a priori and we talked about association rules, there was nothing in there about correlations. It was all just about support and confidence. So what we have to do is we have to go a little bit beyond that. So, so to that end, what we need to do is first we need to think, well, how do correlations show up in data mining? And so let's take just a sketch. Let's say we have a 4-feature data set. And it doesn't matter if one of these is the class or not. With association rules, we don't have a class, but it doesn't matter. So we can think about 4 features, and we know that correlations are defined as the deviations of 2 different features. So we can have a correlation for feature 1 with feature 1, and we can say, well, have we seen that before? And yeah, this ends up being the standard deviation. But we can also have a correlation with feature 1 and feature 2, 1 with feature 1 and feature 3, 1 and 4. So you get the idea. We can make a table or a matrix of correlations. And if we don't talk while we're doing it, we may even make it correctly and write correct things down. But I didn't. So let's try this one more time. There we go. So we can do this. We can write this stuff down all day long. And so we can get a whole matrix of these correlations. These are all the things we can calculate for our data set. If you start to wonder, and I can even go one better, and you can say, well, why am I not filling these in down here? That's because the values end up being the same. That it doesn't matter if we look at how is feature 1 and 2 correlated in this way, or how are they correlated here. We get the same value. So we end up with the same thing down here. And then likewise, we get the same thing down here. These values are going to be the same, and so on. So I can keep going with this, but I think you get the idea that we only need to kind of fill in the top half. When we do principal component analysis in Weka, it's going to show us these numbers. But for our data set, these are all the correlations that we can deal with. Of course, when we have more than 4 features, then this table or this matrix is going to get bigger and bigger. If we want to give a name to this thing, it's going to be the correlation matrix. So this is pretty important for principal component analysis. The correlations themselves are going to be important for association rules. And so in the notes with association rules, I give an example which I took from another textbook, but I cited it, so it's okay, that if we just use confidence, we're not always going to get association rules that are in the data mining world called interesting rules. And so interesting rules just means that we actually get new useful information, and moreover information that's accurate, or in the business sense, information that would be profitable for us. If we just use support and confidence, we can get misled. And so with association rules, there's actually 2 other measures that are used a little bit more often or a little bit more usefully than support and confidence. And so this is kind of the advanced stuff in the course that, particularly if you're doing association rule mining for the project, might be helpful. And those 2 things, those 2 metrics are lift and leverage. If we want to talk about them, we're going to consider a rule like if X, then Y, where we have items X and Y. So X could be an item like if outlook equals sunny, and then Y could be something like humidity equals false, or play is equal to no, just any item like that. And so the way we talked about the confidence, the way we defined it was the same as the accuracy of the rule. And so we talked about that. It was the cover of both of the items, the antecedent and the consequent, and then we divided it by the cover of the antecedent. So we ended up with something like this. So the tie-in between things like confidence and support and correlations, the tie-in with that is that the cover or the support is related to a likelihood. And that's something that we've already seen talking about naive Bayes. And so I'm trying to make a little more whiteboard space here. So support, that thing where we use T and then in parentheses put some items, is related to likelihood or probability or deviations. And so the way it's related, if we have something like the support of x and y, and then we divide it by the number of instances n, and so we're going to have a data set with capital N instances. What that is that's an estimate for a probability, the probability that both x and y are true. So the support divided by the number of instances is related to a probability. And so what we can do with the confidence, we could actually say, okay, I can do one of those math class things where I'm just going to multiply by 1 or divide by n over n, which is equal to 1. And so what we end up with is that the confidence is actually related to probabilities. And this right here, this is kind of the cutoff for undergraduate data mining where you get to graduate data mining. That association rules and lots of other things are talked about as likelihoods instead of just counting instances and calculating supports and covers and things like that. But this is the starting point for the more advanced metrics for association rules. So at this point, I'm going to blank the screen. We're going to talk about the first one, the lift. I'm going to write down the definition of it, and we'll see how it relates to what's been talked about before. So the definition in words for a rule, the lift is the confidence divided by the support of the consequent. So what we saw in the previous slide is that the confidence, and so our rule, if I want a reminder, if x, then y, what that means is the lift is going to be the confidence or the accuracy of the rule. So that's the support of both of these things divided by the support of the antecedent. But notice that the consequent doesn't appear down here when we're talking about accuracy. What lifts us to do is, okay, divide that by the consequent as well. And then what we end up with at that point is we have something that kind of depends on everything in all possible ways. This is where they appear together up in the numerator, x and y. And then here it's the number of instances where x appears, the number of instances where y appears. The reason that's useful is that if we kind of think about that thing that we just saw at the end of the last slide, that, well, these things are actually related to likelihoods, then we can look at this thing, the one on the top, p of x and y, and we can say, well, if x and y are statistically independent, then what we know is that p of x and y is the same as the two products. When they're correlated, though, that's the tie-in to what we've been talking about. When they're correlated, this is not the case. So when they're statistically independent, we get a lift of 1. When they're uncorrelated, then we actually end up getting a lift of 0. And when they're correlated, when it's useful, we get a lift bigger than 1. So if I want to summarize that, we know what the lift is based on. So when it's bigger than 1, that means x and y are correlated. And so that means our association rule is going to be useful or interesting. The bigger it is, the more interesting it is. When it's equal to 1, then that means that what we're looking at is statistically independent. And so if we have a rule, if x then y, and we know that, well, the way x changes has no impact on the value of y, then we would think, oh, okay, so this is a bad rule. And if we have lifts that are less than 1, that actually means that they're negatively correlated. And this is what the example in the notes is, and that means that the rule is not only bad, but even worse, it's misleading. It's one of those cases where if you are not careful dealing with statistics, then they can lie. So for association rules, really, these are the ones we want to keep, the one where the lift is greater than 1. So at this point, I'll take a break. I'm going to make a video that shows you how to deal with this in Wicca and also talk about the leverage.